Welcome to Ask and Learn.
We have this bar hanging from a pivot point here, and then we have a couple springs keeping it in place. And it's also, we have gravity acting, so it's kind of it's a pendulum. And then we have an applied force down at the bottom that's a function of time. It's a harmonic function, and it's F naught sine omega t. So if we just do take moments about this point and go through everything, I'm not going to go through the details here. We get this equation governing the motion of this, of the angle here, theta. 1/3 ml squared is the mass moment of inertia of this uniform bar about this point. And then we have gravitational force and also spring force here acting. And let's see here, I think I forgot to write a 2 in here. Yeah. No, did I? I think I may have forgotten a 2 in that. Let me check here. Let's see here. No, I did not. Why did I not? Oh, I know why. Because this is yeah. It is this term was k times L over 2 all squared, and then multiply it by 2, and that's why we get the half. Okay, yep. That makes sense now. I didn't mess that up. So we can cancel out an L everywhere, and so our equivalent mass is 1/3 ml. Our equivalent stiffness is 1/2 times the quantity mg plus kl. Natural frequency is this divided by this. Frequency ratio is the forcing frequency divided by the natural frequency. The static deflection is the amplitude of the force, whatever in the front of the harmonic term in the forcing function here. So that turns out to be F naught over KEQ. This. Our particular solution is given by this, and what we were asked to find is the amplitude of that, and so that's just this value here. Now we can substitute r in here and multiply numerator and denominator by omega n squared to get this. And so then we have delta static, we plug it in, omega n squared we have is just KEQ over MEQ. And then we have omega n squared minus capital omega squared, the forcing frequency. And what I did, let's see here, this KEQ and this KEQ cancels out. And so then we can, and this, we bring the ml down here, and it cancels with this, and then multiplies this times ml, and this is the expression we get. This is the amplitude. And we can check a few things, I suppose. If k goes to 0, then that goes away, and we still get a harmonic motion because we still have a pendulum. If L, let's see here, if L went to 0, things would be very weird, because basically everything would collapse, and the springs would be acting at the pivot point, and the force would be acting at the pivot point, so we get nothing really happening. Yeah, well, and in fact, one of the problems would be why it doesn't look like this goes to 0 is because I canceled out an L up here. And if L were 0, I could not do that. In fact, if L were 0, then we just wind up with 0 equals 0 here. And so that's why I implicitly assumed after this point that L was not equal to 0. So we can't really take a look at that limit.